Hello. Okay, we're going to look at lesson 4.3, logarithmic functions, which are the log functions. Um, every one-to-one function has an inverse that is also a function. So we need to define one-to-one. So a one-to-one function would be each x value corresponds to a unique y value. So what does that mean? It passes both the vertical line test and horizontal line test. So let's look at an example here. If I draw a quadratic function here, we know that it passes the vertical line test, so that one is okay. But when we do the horizontal line test, it does not pass. So vertical line test is okay, passed. Horizontal line test is not. So this is not one-to-one function. Okay, next, exponential functions are one-to-one functions. Their inverses are the log functions. So how do you find the inverse of a function? What we do is we switch x and y and solve. And then what we do is we exchange domain and range. Okay, so let's look over here. We have the parent exponential function base 2 and its inverse log function. So we're going to set a couple of values for x, -2, -1, 0, 1, and 2. So 2 to the power of -2 is 1/4. 2 to the power of -1 is a half. 2 to the power of 0 is going to be a 1. And then 2 to the power of 1 is a 2. And 2 to the power of 2 is a 4. Okay, so if we graph the f of x equals 2 to the power of x, it's gonna look, oops, that's not, no, it is, yes. 2 and 1, 2, 3, 4 here. And then it keeps going down here. So our f of x 2 to the power of x looks something like this. Okay, so what is the domain for this? It keeps going and going in both directions for the x. So it's all real numbers, -infinity to infinity. For the range, we can see that it approaches the x-axis but never touches it. So it's going to be 0 to infinity. So for this one, we have a horizontal asymptote, which is y equals 0. Okay, let's look at the log base 2x. Now, what actually happens is that we're gonna reverse, since we know that it's the inverse. Remember, over here, switch x and y. So that's what we're gonna do. So we're gonna our first value of x is gonna be 1/4, and that's gonna y is gonna be -2. We flip the y and the x. We do the same for the half. So x is half, our y is -1. X is 1, our y is 0, our x is 2, our y is 1, and our x is 4, our y is 2. Okay, so let's go ahead and graph that. So we have 1 and 0 right here, and then we've got 2 and 1, and 4, 2, 3, 4, and 2 right here. And then we keep coming closer and closer to the y-axis, but it will never reach it. So this is our g of x equals the log with base 2 of x. Okay, we'll talk more about the log, but that's basically what we're doing. So the same thing here with our domain and range. We exchange it. So our domain for our log function is going to be 0 to infinity, and our range is going to be -infinity to infinity. If we look at the graph, that looks pretty much, I mean, it looks correct. It's going to, we have a vertical asymptote here, which is x equals 0, and then it keeps going down to -infinity and up to infinity. Okay, the one thing that we could do is do a line over here between. If we folded this graph along this line, our graphs would go on top of each other. So this line is y equals x. They are symmetric across that. Okay, so that's what it looks like. Now, let's get the definition of a log. So the answer to the log function is always the exponent of the base. That is the answer to the log function. So if we have a base a, y equals log with a base a of x, that means that it is a to the power of y equals x. So let me rewrite this. So we've got y equals this y, when we're talking about the log function, that y is our exponent in the exponential function. So log with a base a, so our base is a, that means that for the exponential function, the a is the base as well. And then the x here is the argument for the exponential function. So that's the answer to the exponential function. So that's what we need to kind of keep in mind. And we're going to look at now. There are three pieces of information that switch places when converting from an exponential function to its inverse log function and back. Again, let me make sure that we have our base here with the log. The base is um, a subscript. It's like down on the bottom with a little bit smaller. And then our exponent. Our exponent is, of course, with the base on top of that. And the exponent is the answer to the log function. And then what do we have left? We have our argument, so our answer to the base to the power of the exponent. That argument goes over here by the log. Okay, so let's look at an example. If we have 2 to the power of 3, we know that this equals 8. So when we are going to write this as a log, our base is 2, our argument is 8, and our exponent is 3. Okay, now we're going to practice this. So we're going to practice writing each equation in the log form. So we're doing the exact thing that we've been doing over here. So we have 4 to the power of negative 3 equals 1 over 64. We're going to write our log. Our base here is the 4, and our argument is 1/64. And our exponent is negative 3. Now, this next one, again, we have our log. Our base is the 6,561. Our argument is 9, and our exponent is 1/4. Okay, this next one, 5 to the power of 0 equals 1. So, log with base 5 of 1, that is our argument, equals the exponent, which is a 0. Okay, now we're going to go backwards. So now we have the log, and we need to write it in an exponential form. Well, so this number right here is going to be the base. Here's our exponent, and our answer, the argument, is 8. Again, our base is 3, our exponent is 4, and that equals 81. Okay, for this one, our base is b, our exponent is y, and our argument is x. So remember, the answer to the log function is always the exponent of the base. Now, go ahead and pause the video and practice these problems. Again, remember that you are looking for the exponent here. So the way you want to start doing these, or actually I said pause the video, go and look at a couple of examples and then pause and see if you can get it. So our base here is a 3. Our argument is 9. So what we're going to do is ask ourselves, what 3 to what power equals 9? Well, we know that 3 to the power of 2 equals 9. So our answer is going to be 2. We're going to do the same thing here. So again, 5 to what power equals 625? That might require a little bit of thinking. If we start, 5 times 5 is 25. Then if we multiply this by 5, we get 125. If we multiply this by 5, we get 625. So how many did we have? 1, 2, 3, 4. So 4 is the answer. 5 to the power of 4 equals 625. Okay, number 3. Again, 6 to what power is 216? And you have your calculator as well. So you can, start plugging in numbers here. It is 6 to the power of 3. That equals 216. So our answer is going to be the 3. Okay, number 4. Now, 9 is the base and 3 is the argument. So what number or what is the exponent of 9 that we get 3? Well, if we do square root of 9, that would be 3. Square root, remember, we can rewrite it as to the power of half. So our answer for this one is a half. Okay, next one. Base is 2, and our answer is -4. So what number to the power, or what 2 to the what power equals -4? Well, can we have a negative without having a negative base? No, we cannot. So this is not possible. Okay, next one is 3. So 3 to what power equals 0? Well, there's no such number because we know that 3 to the power of 0 equals 1. So again, this is not possible. All right, next. Again, 2 to what power equals 1/4? Well, it's going to have to be a negative because we have the answer is 1/4. So 2 to what power equals 4? That would be a 2. So our answer is -2. All right, our base this time is a half. To what power? It equals an 8. Again, in order for us to go from a half, a fraction, to an 8, our answer is going to have to be a negative. And then 2 to what power is 8? It would be 2 to the power of 3. So -3. Now, for number 9, 4 to what power equals 1/16? Again, it's going to have to be a negative because it's 1 over something. And then 4 to the power of 2 equals 16. So it's -2. Okay, same thing here. Log with the base 7 of 49. So 7 to what power equals 49? Well, that's going to be 2. Next one, 4 to what power equals 1/4? Well, again, it's 1/4. It's the reciprocal of 4, so it has to be a -1. And this last one, log with base 9 of 1/81. So again, we have a 1 over, so it's going to have to be a negative. And then 9 to what power is 81? That is a 2. So every single time our argument is 1 over something, you know that the exponent has to be a negative, and for our log function, our answer is going to have to be a negative. Okay, now for the calculator, there is no such thing as any base. But what we can do is we can evaluate logs in 2 special bases. So our 2 special bases are base 10, and on the calculator, it is the log button. This means, and this is called the common log. So if you see log like this, it means that it is log with base 10. Okay, the other one is the natural log. So that is base E, and that one is ln on your calculator. So a log with base E equals the natural log, which is ln. And notice that I didn't, like, yeah. Anyways, never mind. Okay, simplify each common log without using your calculator. So common log means that base is 10. So 10 to the power of what equals 1,000? Well, tens are easy because as many zeros as we have, 1, 2, and 3, it's going to be the exponent. So common log of 1,000 is going to be 3. Same thing here. Um, we've got 1, 2, 3, 4, and 5 zeros. So the base is going to be, or not the base, the exponent. The answer to the common log is going to be 5. Now, this next one is a little bit trickier because we have a decimal actually. A decimal is smaller than 1, so we're going to have a negative here. And if we move the decimal 1, 2, and 3 all the way to where, to the right of the 1, we get our exponent. So our answer is going to be -3 for that one. So how did you know these were all common logs other than it saying it over here? Actually, I used to, like, it did say it here, but how would we know without it saying? It is because it's just log. There is no base. Okay, let's look at simplifying each natural log, and now we're going to use the calculator. So again, on the calculator, you have the ln button. It is, and I should have grabbed it's on the right, on the left, sorry. If you go from the top of the calculator, so you've got your calculator screen right here. On the left here, you have a second. Then this next button is the log, and the third one is the ln. So this is what you're going to be pressing. You'll press ln, and then you'll press 1. Well, that answer is going to be a 0 because even though we have a base e, any base to the power of 0 is going to equal 1. So we know that that's going to be a 0. Now, for the natural log of 10, you get 2.303. For the natural log of -6, you're going to get a syntax error. That is not possible. Um, remember that, or we will never have a negative argument. Again, the argument is this here because base must be positive. Remember here when we graphed the log, it's um, well, this doesn't actually show the base. We'll look at it, but anyways, never mind. With the 2, it shows that it has to be, but your base has to be always a positive with the log. Now, how did you know that these were all natural logs apart from it saying that it is a natural log? Um, that is because it had the ln and again, no base. We still, even though there is no base, we know that it is because of the ln here. Okay, there isn't an any base log button on your calculator, so how can we find an approximate answer to log problems in other bases? So what we're going to do is we're going to use the change of base theorem. So for any positive numbers a and x with a that does not equal 1, we have the log base a of x can be written as natural log of x over natural log of a. We can also write it as a common log of x over common log of a. Now, notice that a is the base here, so a goes down here, and then x is the argument, and x stays where it is. So the base always goes to the bottom. Okay, so practice. Use the change of base property to simplify or solve and find an approximate value. Round answers to 2 decimal places. So we're gonna first do it with the common log. So common log of 56 over the base common log of 3. And when we do this, we get 3.66 on the calculator. Now, let's do the same thing here and try it with the natural log of 56 over the natural log of 3. When you plug that in, you get the exact same answer, 3.66. Okay, let's do this next one. Our log, or the base is 0.2, and our argument is 9. So we would do the natural log of 9 over the natural log of 0.2. And when we put it in the calculator, we get negative 1.37. Okay, this next one, number 3, we have it as the x is as an exponent. So we are not able to plug this in the calculator in any way with this form. What we need to do is we need to change it into a log first. So log and our base is 5.44. Our argument is 2.3 and our exponent is x. See how the x is out here, and we can solve actually this. So x equals common log of 2.3 divided by the common log of 5.44. And when we plug it in the calculator, we get 0.49. So we needed 2 steps. We needed to go from the exponential form to the log form and then use the change of base theorem for that one. Okay, let's do one more here. So again, we need to do the same steps that we did in 3 because the x is in the exponent. So log, our base is 10 right here, of 3.91, and our exponent is x. So we do the same thing, a change of base. Log, actually, yeah, log of 3.91 over a common log and common log of 10. Well, common log of 10 is what? That is a 1, so 0.59. Now, could we have just plug this in the calculator? Yes, we could have. Notice that the base is 10, So this is already in the common log form. So we really didn't need the change of base here. All we needed to do was to plug that in the calculator. Okay, properties of logs from definition of log. Um, so we're gonna let x and a be any positive real numbers with a that does not equal 1 and r be any real number. So if we look at our a first, so log with any base of 1 equals 0. So that means that, for example, if we have log with base 8 of 1 equals 0, and that is because 8 to the power of 0 is always 1, right? That comes from there. Our next one is b, log with the base and the argument being the same, that's going to equal 1. So if we have log of base 12 of 12, that's going to equal 1. That is because if our base is 12 and our exponent is 1, our argument is going to be the 12. Okay, next one is C. So if we have a log with the same base and argument to the power of r, our answer is going to be r. So log with the base 5 of 5 to the power of 3 is going to be 3. So what does this mean? We have the base 5 here, and we have 5 to the power of 3 as the argument. So our question is, what is the exponent of the 5 so that it equals 5 to the power of 3? Well, if our bases are the same, it's going to be the 3. Okay, and then let's look at D here. So a to the power of log with the base a of x equals x. So this means that, hold on, no. 2, for example, 2 to the power of log with base 2 of x is going to equal x. There's really, yeah. So what you need to do is you need to memorize these properties of the logs, A, B, C, and D. Now, again, remember that logs are the inverse of exponential functions. This means that the properties for logs are going to be related to the rules for exponents. So if you think about the product rule, when you are multiplying the base, we add the exponents, right? 2 to the, if we have 2 to the power of 3 times 2 to the power of 4, we do 2 to the power of 3 plus 4, which is 2 to the power of 7, right? Now, our quotient rule is when you are dividing the base, we subtract the exponents. So if we have 3 to the power of 5 over 3 to the power of 2, we do 3 to the power of 5 minus 2, which is 3 to the power of 3. Okay? The third one is the power rule. So when you raise an exponent to a power, you multiply the exponents. So, for example, 4 to the power of 2 to the power of 5, we would do 4 to the power of 2 times 5, which is 4 to the power 10th power. So we will use the rules for logs to help us expand and condense log statements to see if we can simplify any of the expressions. So the product, quotient, and power properties right here. So Again, a cannot equal 1 and r is any real number. Our product property says that if we have x times y as the argument, we can write it with two separate logs. Our quotient property says that if we have the argument has a fraction or division, we can write it with two separate logs with subtracting. Remember here, for the quotient rule, we subtracted the exponents. That is why we're subtracting here the logs. We are adding the logs here because for the product rule of the exponents, we added the exponents. Okay, the power property is a little bit different. So if we have the exponent r here in the log, we can bring it down to the front. Again, these are something that you're gonna have to know. Okay, let's practice here. So use rules for logs to expand each statement. Simplify when you can. Um, we have a division, so we're going to use the quotient property here. So log with base 3 of 27 minus log of base 3 of 4. Now, can we simplify something here? This thing here, 3 to what power is 27? Well, 3 to the power of 3 is 27, so we can simplify it to 3 minus log of base 3 of 4. And that would be your simplest answer. Now, our next one has a multiplication here, so we're going to use the product property. So natural log of 3 plus natural log of x squared plus natural log of y. Now, we can take it one step still. For the exponent 2, we can use the power property. And we get natural log of 3 plus 2 times natural log of x plus natural log of y. And that's it. Okay, next what we did here is we expanded. Now we're going to use the rules for logs to condense to a single expression. So we're going backwards. So for example, this first one, we have an addition here. We have the same base, which is the common log. So what we're going to do is we're going to use the product property, but backwards. So common log 25 times 4. 25 times 4 is 100. Now remember that we have a common log, so the base is 10. 10 to what power is 100? We count the zeros and we get 2 as our answer. So this is why we sometimes do these. And again, expanding might help, and sometimes condensing might help to do these calculations. Okay, this next one has quite a bit. What we need to do first is we need to take this 2 and use the power property backwards. So we're going to rewrite it as natural log of x squared plus, and we're going to do the same thing for this 1/3. We're going to put it as an exponent here, like this. Now, our next step is that we have the plus here, so we can actually use the product property backwards, the other way around, from right to left. So, natural log of x squared times x plus 5 to the power of 1/3. And we can leave it in this form. Also, we can remember that 1/3 is a cube root, so we can do cube root of x plus 5 like this. And everything that is in the argument of the log has to be inside parentheses. Otherwise, if we didn't use parentheses, we could think that this would be only natural log of x squared times cube root of x plus 5. So that we would only apply the natural log for this part here and not for the rest. So everything needs to be inside parentheses to be clear that that's where it is. Okay, that's it for this lesson. Let me know if you've got any questions. Bye.